So this goes back, the observations go back a few years, but recently became somewhat popularized when an archive paper appeared showing that, among other things, consecutive primes seem not to often to have the same last digit. So, for instance, you'll find that in the second, well, okay, in the first 10 to the 8 pairs, no, 10 to the 8 pair. There's something messed up in the numbers there, but I think up to 10 to the 8, there's 4.6 million pairs that end with 1, 1, but quite a lot more ending with 1, 3. And similar for 1, 7, 1, 9, it drops back somewhat. And the obvious explanation isn't the right one. The obvious explanation is, well, you have a chance if your number ends in 1, 3 comes up sooner than 1 comes up again as the last digit. And so probabilistically, maybe this is expected. But if you run the probabilities, it doesn't come close to explaining the discrepancies. Okay, so in the fine print mention, there was some prior work that came to my attention only a few days ago, mostly because I didn't read the references carefully when I should have. And so there are some similar results. The work by Ashveltis, Gross, Sinan is related, but not really quite. They go in a somewhat different direction. Okay, so I want to cover 3 cases to try to illustrate what's happening. We'll first look at last digits mod 3, then mod 4, then mod 10, and I'm going to try to bring out different, get successively more involved in each of these. So mod 3, we look at the second million primes. Why? It was a convenient set to work with for a number of reasons. Not too important the detail. So the number that ends in 1, 1 is about 220,000, 219,000. Mod 3 we're talking. So we can have the last digit be 1 or 2. The pairs that go 1, 2, it's 280 plus thousand. So that's a lot different. And 2, 1, similar, 2, 2, back down to about 220,000. So the ratio of, say, 2 2s versus 2 1s is around 0.78. And this was considered to be unexpected. If you expect this, the talk probably isn't going to interest you very much. It'll just be confirmation bias or something. Okay, so I want to show that this is actually a sensible result and give some idea of what happens. So mod 4, I just want to show it's a similar story. And actually very similar. Now we're talking last digit has to be either 1 or 3. Everything else is even. Okay. And by the way, there's the anti-diagonal, you see this very strong symmetry. Well, the numbers are identical in this case. Usually they're very close in those computations that have been done. That's not something I'm going to try to explain, but the work by Ash and co-authors does get into that heavily. Okay, mod 10. So now we have 4 cases for the last digit of a prime, and so 16 cases for pairs. 1, 1, 1, 3, etc. All the odds except 5, basically. And so what happened? Well, we're going to focus on the top row. I'm not going to worry about the others elsewhere in the talk. I just wanted to show them all. So the top row, we have 44,000 that end in 1, 1, 76,000 in 1, 3. 1, 7, the number actually goes up to almost 78,000, which I think is some evidence that it's not just the proximity that causes 1, 3 to be more likely than 1, 1, because then 1, 7 would have dropped more. And at 1, 9, we go back down towards, now only 52,000 or so. And there'll be reasons that'll become apparent for this. Okay. Answer yes. What was the question? Okay. Yeah, all right. Will we explain this? I hope to. I mean, yes, I'm going to explain it. Will my explanation be clear or not? Well, depends on how much coffee did to me earlier, I guess. Okay, so the first row, okay, so I'm going to start with consecutive pairs mod 3, and I realize this slide is fairly early in the game. I'm going to spend a little time belaboring it, though some of the others will go somewhat quicker. So, equivalence classes, okay, we're looking mod 3, so what I'm going to do is look at equivalence classes modulo the next prime, 5. Great. Okay, and we're going to generate a probabilistic model for when primes, how often primes appear that are in certain equivalence residue classes, and that will give us some information. So, we're going to only focus on the case where the first prime equals 1 modulo 3. The case where it's 2, it would be a similar analysis. I'm not going to go over it at all. Okay. Now, obviously, the value is equal to 1 mod 2 since there's no evens in the second million prime. So okay. So 5 is the next prime of interest, and there's 4 relevant cases. We have to be equal to 1, 2, 3, or 4 mod 5 because otherwise we're definitely composite. Okay. So if P1 ends in 1 mod 3, then P1 plus 2 has to be composite. It's divisible by 3. P1 plus 4 is composite for certain if P1 was equal to 1 modulo 5. And that happens 1/4 of the time, assuming, you know, if that doesn't happen 1/4 of the time, there's, yeah, number theory has other things to worry about than just this, you know, the topic of this talk. Okay, so similar cases come up. P1 plus 8 is composite if P1 was equal to 2 mod 5. But that case was forced anyway, because we know it's divisible by 3. P1 plus 6 is composite if P1 is 4. The first prime is 4 modulo 5, which again happens 1/4 of the time. Okay, so who's missing? Well, P1 plus 10 didn't show up in the list. Oh, P1 plus 12, 14, 16, 18 are going to, similar things are going to happen because we've just added a multiple of 5, 2 times 5, to the earlier cases. So P1 plus 10 didn't show up on that list, and that's going to be important. That's going to play a role in the bias that appears. Okay, and the reason it doesn't show up, of course, is because P1 plus 10 can never be forced to be composite based on residue class mod 5. Okay. So, okay, so P1 plus 2, just to go over it, has to be composite because 3 divides it. 1 in 4 cases make P1 plus 4, 6, or plus 8 composite. Same with 12, 14, 16, 18. P1 plus 10 is never forced to be composite due to the residue class mod 5, to recap. Okay, so our probability model for the second prime, P2, in a pair, goes like this. We know it's not 2, so we start with what is the probability that P1 plus 4 is prime, and we step through it. 1 in 4 cases forces it to be composite, 1 in 4 of the residue class is mod 5. So it should be 3/4 of the conditional probability that no prime larger than 5 divides it. In a reasonable, you know, probabilistic model of you know, 1 over log n numbers are at random prime. Okay, so there's a conditional probability here, though, because we know this number we're looking at is not divisible by 2 or 3, and we're assuming that we're in the 3 out of 4 cases where we know 5 isn't. Yeah. Okay. So we're going to, in the back of our minds, assume that we're in a size range. I'm calling it n for this set of examples that we looked at earlier, n is about 1 million. Okay, so we have to throw in a factor of 1 over log n for probability that a number is prime. And there's other factors, the density of numbers. We know it's not divisible by 2, 3, or 5, and that accounts for 4 out of 15 numbers. So 15, there's going to be a reciprocal of that factor. And, okay, so the probability, and we have the 3/4 because of the 3 out of 4 residue classes, mod 5. Well, we went through that. Okay, so the probability that P1 plus 4 is a prime is given as such. P1, the probability that P1 plus 6 is the first prime after P1 goes as follows. We have to rule out the case that P1 plus 4 was prime, because then that would have been the first successor. And so we have 1 minus that probability, and again times 3/4 times 15/4 times 1 over log n. That's our estimated probability. Similar for P2 equals P1 plus 8, we have to subtract off the probabilities of both the prior possibilities, P1 plus 4, P1 plus 6, and we have that factor. P1 plus 10, this is the different case, the first different case. We don't have that factor of 3/4 because P1 plus 10 is not forced to be composite 1/4 of the time. Okay. And P1 plus 8 was necessarily composite, so that contributes nothing to the probability. So the probability that P1 plus 10 is the next prime is, if I can use my laser pointer, so 1 minus probability that it was 4, probability that it was 6, times, I wrote 5/4, that was a typo, that should have been 15/4, times 1 over log n. What's missing is the 3/4 factor. We have a bump here, in a sense, unexpected increase in the probability. Okay, so we could continue this as far as we need to. Well, there's a few things that I'm not going to show in this particular example. One, I'm not going to worry about residue classes modulo larger primes, 7, 11, etc. Okay, and since our primes are in the vicinity of 10 to the 7, I'm going to assume that most cases we will find the successor prime when we only go to about log of 10 to the 7 or some small multiple thereof of log of 10 to the 7 to have a probability almost 1 that we have found our successor. And so the next slide is some code, mathematical code. And this extra factors list just records how to alter probabilities after we've taken into account the 15/4 and the 3/4 and the 1 over log n. And so for P1 plus 2, you'll see there's a 0 because we know that that's composite. The next two don't get alterations. P1 plus 8, I'm skipping 2. So the first in the extra factors corresponds to P1 plus 2, then P1 plus 4, P1 plus 6. P1 plus 10 is the first guy to get a bump. And it's a factor of 4/3 to offset the 3/4 that is in the common multiplier that I'm calling most there. And so this was some very pedestrian code that I probably would be denounced at work for having shown because it has a do loop in it. And well, okay, we won't get into that. And so the numbers showing up in the output, don't really worry about them too much, but the one at the bottom just shows that we have hit about 96% probability of having found our successor prime. That's good enough for what we're doing today. I mean, this is supposed to be crude estimates. So the probability that P1 plus 4 was the next prime is 0.17 roughly. 17%, 14% for P1 plus 6, 15%. P1 plus 10 takes a drop. And, okay, that was because of the alteration that we covered earlier. Okay, so the next step, well, we want to compare residue classes mod 3, so we only have 2 possibilities, 1 and 2. And we are assuming that P1 equals 1 mod 2. So we're going to look at P1 plus 6, P1 plus 12 are the cases that P2, if those are the first successor primes, those contribute to the case where P2 equals 1 mod 3. And we sum all those to get that probability. The case where P2 equals 2 mod 3, are the cases where P2 is P1 plus 4, P1 plus 10, et cetera. So we're summing the second, fifth, eighth, et cetera, from the list. And we just do that. And when we take the ratio of the two, we get it's 76.7, so almost 77% different. I mean, the ratio of the 1-1 case, which happens less frequently, happens 77% as often as the 1-2 case. And the actual, that's just from our estimate, our crude estimate. And the actual situation was that it's about 78%. So the model seems to be reasonably useful. And we didn't even go very far with residue classes. Okay. So, let's see. Consecutive pairs mod 4. I'm not going to cover that now. It's going to show up later in a bigger, better, badder way. Okay, mod 10. This is similar to the last case, but I'm going to take it further. Same idea, but further. Okay, so we're again going to focus on the first prime equal to 1 mod 10, and okay. So the other possibilities are 3, 7, or 9, not 5. And because 5 isn't a prime, we're going to have things that end in 5. I didn't really say that.
You did.
End in corner. Okay.
It's recorded too.
Yeah, that was yeah, okay. All right. Sorry. Because numbers that end in 5, except for 5, are not prime, we don't worry about, there's going to be zeros showing up in our list. Okay. Y'all heard it here for the first and I hope last time. Okay. So we're going to use a bunch of moduli this time. We're going to refine the estimates, 37, 11, 13. Okay. And we're going to modify our probability, the 1 over log n. We now have a factor of, well, for these residue classes, so there's going to be a 1 and 2 for the mod 3 times a 5 and 6 for mod 7. Equivalence class is mod 7 because one class can't happen. It's definitely composite, and et cetera. And we also have to account for the fact that we know the numbers aren't divisible by 2, 3, 5, 7, et cetera. So that's a computable fraction that will show up. But it's computable by an easy recurrence. And so some code, and the numbers are just to show how many primes I went to, and that fraction is the fraction that's going to show up as a modifier because of the conditional probability stuff. And okay, so I guess again the numbers, it's just code I ran that's well, okay. So what happens is the important person in this output here is the list at the bottom. That's the modification factors. Again, there's a lot of ones. There's a twos that show up every third because modulo 3 shows up every third, and we get a bump in probability from not having compositeness ever forced on us half the time in those cases. And similar, we have other modification factors. I was 6/5 doesn't show up earlier simply because it shows up in the same spot as a 0, and 0 times 6/5, so it's still 0. Okay, and so, whoops. Okay, so here I want to belabor a point. So we've used several primes other than 2. Okay, great. So let's look at what 3 does. Residue class is mod 3. It can't divide P1 plus 6, 12, 18, 24, 30. 7 can't divide P1 plus 14, 28, 42, 56, 70. The important point is we get back to P1 plus 30 is going to have the same last digit as P1. So 3 does not increase the probabilities for for the next prime having the same last digit as the current one until after it has already increased the probabilities for every other case. Likewise for 7. And this is true for all other primes. So the takeaway point here is that this basically gives the qualitative explanation for the biases that we've been seeing. Okay, so the rest of this is just an attempt to help quantify. Probability estimates, so this time I go to almost 100%. And something interesting does come up from all this. Wasn't as high as I thought, okay, almost 99%. Okay, and so I do the sums and all that. Now, what's interesting, I mean, the ratios, 0.54, et cetera, may not make much sense. But when here's the estimated ratios and here's the actual ratios. So 2 successor primes, both ending in 1, is 58% as likely as successor primes ending in 1,3, 56% as likely as 1,7, 85% as likely as 1,9. What's interesting is that this model actually overpredicted the bias, and I don't know why. So there's probably still some funkiness in the model. There may be a factor I'm losing somewhere. Anyway, yeah, so we're getting, if we invert those last numbers, 1.8 instead of 1.7, 1.85 instead of 1.72, 1.3 something instead of 1.17. So the method seems to be on track, but imperfect. Now, for the finale, I hope. I saved mod 4 because it's a somewhat easier case. We don't have these zeros ever interspersed. And I wanted to try to do a asymptotic analysis. And here's where some symbolic computation comes in for real. Okay, so what I'm going to do, mod 4, is I'm only going to consider a couple of primes. Well, let's see. Oops, sorry. We're going to consider an unspecified but large value of m and ask what are the relative densities of our successor pairs as we go from m to 2m, so that our primes are all in the same rough size range, and what do we expect for the behavior of these fractions of ratios of successor pairs. And so we know that we have to get most of the successor pairs, we have to sum to, well, it's actually a multiple of log n, like 3 log m or something from P1. But whatever, that doesn't really, it's not going to change things. Okay, so our probability corrections, we have a factor of 1 over log m. Again, I know that's crude, use a log integral, but this will be fine for our purposes. And we have to account for the fraction, this conditional probability fraction that has been thrown in. And so we get a formula, and it's a pretty awkward recurrence. The probability that the n plus first possibility is our successors, 1 minus the probabilities of all the priors, times some fractions, times these modification factors, prime j minus 2 over prime j minus 1, a product of those. And then we have this really awkward last guy, when you saw the 1/2 and 6/5 and fractions like that before, and I don't know how to estimate that, and I'm not even going to try. Some of the others we could estimate, but again, it's going to turn out we don't need to. I'm only going to work with equivalence classes mod 3 and 5. And so that gives me a factor of just 1/2 times 3/4. And this last thing here, I can substitute for that a piecewise function where I have a 4/3 if I'm equal to 0 mod 5 and a factor of 2 if something similar happens mod 3. And okay, so what can I do with that recurrence? Oh, I also had this recurrence depended on all prior probabilities, but you'd like a recurrence where it's just maybe 2 terms or so. And we can do that because this happens to have a dependency in the nicest possible way. It's just an unweighted sum of all priors. So I make a new function. So g of n is the sum of pj's from 1 to n, those probabilities. And now my recurrence really only involves 2 terms, g of n plus 1 and g of n. P of n plus 1 equals g of n plus 1 minus g of n. And, okay, so I get this somewhat nicer, well, it's not nicer yet, but when I do the simplifications of only looking at residue classes mod 3 and 5, I get this somewhat nicer formula. Okay, more code. I can solve that recurrence. It takes Mathematica a while, and it's not a very pretty solution, and you can't see it, but you have to, because I have to shrink it. But take my word for it, if I expanded it, it wouldn't get any prettier. Okay, now what I can do, though, is because we're assuming m is large, this value k, it can be, I hid all the factors independent of n, I lumped them together, I called it k. It's something, it's easy to show that it's very small if m is sufficiently large, and okay. So I can take a series estimate at infinity, which is what I do, and just take first order estimate, and okay, now I get something that looks somewhat more tractable. Okay. And, okay, there's a little more messing around to go to handle the cases where, to get the right values for where the probability, our successor prime is equal to 1 versus 3 mod 4. Okay, and this computation also takes a while, and so that, there's an enforced coffee break and all that. And
Double.
okay, some things I couldn't quite resist. Sorry. Whoops. I have an extra page in there. Okay. Fine. Now we do some simplifications. There's this large value of m that we're going to sum to log m or a small multiple log m. And I'm going to do some simplifications by pretending that it's a multiple of 15, even though it isn't in general. I'm sorry. I'll hurry. And okay. And so after some simplifications, I get, and this is really nice, this ratio. And so this is my asymptotic approximated ratio. And you'll notice that, first of all, in the limit it's 1, as m is large. We're actually going to substitute a log in there. And secondly, to my surprise at least, there's even no modification term in the denominator. I thought there might be something logarithmic in m there, but there isn't. Okay. And now, just to test it, the computed values from the actual primes, going in this range of the second million primes, the computed value of ratio is 0.79, and what our estimate gave us, yes, there's an imaginary part, but that, yeah. Anyway, let's just have the series worked out and all that. But it's roughly 0.83, so that's reasonably close. Did I make some grievous mistake and just get lucky? Well, I actually compared by using that recurrence without the truncation, running the same numbers, and I got this time 70.79, 79.5%. So this is some confirmation that I actually did all the symbolic machinations correctly. Okay, so this pretty much ends what I wanted to say. I guess what I should say for the asymptotic estimate is what happens if I had used more terms, more primes, more moduli. And would that alter in a significant way the estimate? I don't have a proof for this, but the answer I think is no. I think there's a majorization argument that says basically most of the damage, most of the alteration that can be done was already done by taking into account 3 and 5. So that's it.